through my water level prediction project for the coastal bend region for the course 6380 data analytics. The project uses machine learning and deep learning techniques to predict water level at Packery Channel, which is like critical for the flood prevention, navigation, safety, and coastal management. Now, the problem I am addressing is, can we accurately predict water level at coastal station hours in advance using metallurgical data and historical measurement? This is important because coastal communities need advance warning for flood events. Navigation require accurate water level forecast. Traditional persistence model assume current water level continue, perform purely at long horizon. We need to understand which features drive water level changes. So as you can see, this is my GitHub repository in which I have put down all the codes. And here you can see the README of the project in which basically I am dealing with three types of scenarios, which is like 1 hour nowcasting, 2 hours, and the second scenario is 6 hour, and the third scenario is 12 hour. Okay. So before diving into the code, let me show you how this project is organized. And I'll just move down to my VS Code. So there are four main folders in my project structure, which is like analysis, data, model, and plots. Analysis is where I write most of my scripts. Data basically contains the historic data and the testing data. The model is what models I have tested, plots where all the images are there, and the PDF is basically my presentation, and then you can see the README. So if I open down my analysis project, I have created break down the pipeline into 8 different steps, as we have shown. The rest all codes are my helper codes for the project that I have done. Okay, so uh, each steps build on the previous one. Step 1 to 2 are my data preparation and the feature engineering steps. Step 3 to 5 are model training, which is like baseline, LSTM, GNN, and ensemble models. And same, step 6 is an ensemble creation. Step 7 is my data testing on the blind data, which is like 2025. And then on step 8, we are doing a comprehensive visualization. So moving down to the step 1, where I load and access data quality. This is crucial because real world environment data often has gaps and quality issues. So here are my loader functions and all the things. If you move down up here, this is my water level data for all the station. This is where I'm reading down all the Excel files, which is shown up here. This is like the meat and the water metallurgical and the water level historic data that we have used. Test data is separate because I have to test it at the end, and then the data prepared and the modeling enhanced are my features that I did after my feature engineering. So these contains hourly measurement for multiple coastal monitoring station. I merged them on date and time to create a unified data step with around 30,000 hourly records. Okay, yes. So here, if you can see for the station in WL station missing counts, uh, basically it fills up the data frame, and then missing prediction, basically it comes out to be missing count upon total number of records into 100. If the missing point is less than 5, the quality is excellent. Here I'm doing is I'm basically loading the data blindly. I analyze every station for the percentage of missing data, consecutive gap length, statistical summaries like mean, standard deviation range, and quality qualification. This analysis reveals that station 005, which is like Packery channel 008, 013, and 20 have a good quality data. A good quality data means has less than 10% of missing data. So I'll focus on these stations and leave the rest of the stations that are there. Okay, if you see my code output file, which is on line number, yeah, 315, it saves all the data, saving the data on the merge data.csv and completely merge data.csv. It's up and running up there. This step take around 2 to 5 minutes to run and requires Panda, NumPy, Matplotlib, and Open py-pixel for reading the Excel's file. Okay, this basically saves my data in the data prepared model, complete data you can see up here. Okay, and now moving down to the advanced feature engineering or the feature engineering that we have done for this project. So step two is where I transform raw measurement into a predictive features. This is arguably the most important feature. Good features makes or break your model. So if you come down to this is the tidal constitution that I use. M2. M2 is basically the lunar semidural, and S2 is principal solar semidural, and N2 is large lunar elliptical, and K1 is lunar delunar for me. So, water levels are heavily influenced by tides, which have well-known periodic components. Now, M2 basically the main lunar tide with 12.42 hours period. This is the dominant tidal force that is being used. S2 is solar semidiurnal tide, which is 12-hour period. N2 and K1 other significant tidal component. I encoded this as sine and cosine pair so the model can capture the cylindrical nature. This is the code I developed based on the oceanography literature. These specific periods are well established tidal constitution. If we look at this chunk of our code, wind is a major driver for water level changes through our process called wind setup. I converted wind speed and direction into U and V components. Okay. Now U and V component is north, south, and east, west wind vectors. Wind stress is like proportional to the speed square. This is the actual force of the water along channel winds, which basically winds parallel to the channel, have the strongest effect. This is the standard metallurgical practice I am using to establish formulas, not developing new physics at all. If we come down to the code up here, this is where what I'm trying to do is water doesn't move independently at each station. They have a regional pattern within it. It captured with this. So the gradient is like the difference in water level between station tell us about regional flow. Spatial, the average regional water level, and anomaly is how much Packery deviates from the regional average. These spatial features are crucial for the GNN model later that we have used. Okay, now moving down to the code of temporal features that we have developed. Past water level are strong predictors for the future level. I create a lag feature up here, a rolling statistics and rate of change. Water level 1, 2, 3, 6, 12, 24, and 48 hours ago is the lag features. Moving average and standard deviation over different windows for the rolling statistics, and a rate of change, how quickly the water level is rising or falling. Important for each prediction scenario, I excluded lag that would use future information. For example, the 6-hour prediction cannot use a 1-hour lag. Now come down to the most important part of train test split. Okay. So this is where I split the data temporarily. So training data is from 2021 to 2023. Validation set is complete 2024 year. And test data is like a separate file for me, which I used in the later of the steps. Now I've created 110 feature total and saved them in the directory of, if you can see inside the data, we have modeling enhanced, and in modeling enhanced, you can see the feature.csv. and metadata, training data, and the validation data. This is how my feature looks like. This is the metadata for our target station. This is the training data, which includes from 2021 to 2023, and then the validation data set. Now, coming down to the next step, which is like the baseline model training. So for the baseline model training, I use predictions. So now we get to the modeling part, which is like the training the traditional machine learning model for three scenarios, 1 hour, 6 hour, 12 hour ahead of predictions. If you come down to the scenario part, here I have defined the scenarios for the 1 hour, 6 hour, and the 12 hour with a lag of all the things. Uh, so the notice up here that the execute lag is being implemented for a 6 hour prediction. That means I cannot use lag shorter than the 6 hour because that would be using your a future information and model will know the answers on the immediate basis. This is critical for the real world deployment. Now I use the persistence baseline for my baseline prediction, which is just for the water level. And you can see I have defined the persistent baseline up here. Before using a complex model, I just want to check how the baseline is performing. They just predict the water level will stay the same or not. This is important because that's what the naive forecaster would do. It's surprisingly hard to beat the short horizon. It gives context to our ML improvement. As you'll see in the result, persistence has an RMSE of 1.5 centimeters at 1 hour, 6.8 centimeter at 6 hours, and 10 centimeters at 12 hours. Now moving down to the model execution of xgboost, which is this part. Okay, I use xgboost, a gradient boosting algorithm that becomes an industry standard for tabular data. Key points for this will be I'm using this library, xgboost library, as it is no modification at it. This is an automatic optimization over 50 trials, and I'm using a parameter which is for the tree depth, learning rate, regularization, etc. Each trial trains a model at and evaluates RMSE on the validation dataset. The Optuna library handles the optimization strategy for me. It uses a Bayesian optimization to intelligently search the parameter space. I'm just defining what parameters to tune and their ranges. The XGB objective function takes trial parameter from Optuna, trains an XGBoost model, return validation RMSE. Optuna minimizes this RMSE across all trials. This whole optimization takes me around 20 minutes per scenario to train. Now, coming down to the random forest training, which is been selected. So I used persistent RMSE, which gives me around 1.45 centimeter, surprisingly very much good. Or because it's due to this reason, because in 1 hour there is no certain changes in the water level. That's the reason I'm getting a very good result in persistence. Now XGBoost gives me an RMSE of 2.9 centimeter, which is worse than persistent. And random forest gives me a 2.53 centimeter of RMSE. So at very short horizon, persistence is hard to beat because water level has high inertia in it. Now, coming down to the scenario 2 for all the models, I got an RMSE for the persistent as 6.85. For XGBoost, I got 5.32, which is like 22% improvement. And random forest, I got 5.51 centimeter. For scenario 3, persistence has given me a 10.05 centimeter and RMSE. XGBoost give me a 7.57 centimeter RMSE, which is like 25% improvement. And random forest gives me a 6.86 centimeter, which is like the best performer for me for scenario 3. Now, the complete step 6 took me around 30 minutes for all the three scenario with an opt-in optimization. I'm not using any sort of a GPU. I'm just using my machine, which is MacBook M1, and I'm the data is not very much big, so I'm getting the result as desired. Okay, now let's move down to the step 4, which is like analyzing LSTM on all the scenarios. So previously we did for baseline, which is like the persistent model and our XGBoost model. Now we do it for the LSTM model within hyperparameter tuning. We are using a deep learning with an LSTM, long short-term memory network. They are designed for the sequence data and capture long-term temporal dependency. So this is where I define my class water level LSTM. I'm using a PyTorch to build a custom LSTM architecture. Let me explain each and every component. So I used an input size like the number of feature, which is varies by the scenario due to the lag exclusion. I used a hidden size of 64. Each LSTM cell has 64 unit. This is in the memory. I tried it with 128, but 64 is where I got the lowest RMSE. Then the num layer, which is like two stacked LSTM layer for more capacity. And then dropout of 0.2, which is like 20% between layer, preventing overfitting. So the batch size is true for us because it's formatting choice for the PyTorch. Now how the fully connected layer look like. So FC1, which is like this one, FC1 is like 64 to 32 dimensional reduction with ReLU activation, dropout, another 20% dropout for regularization, and FC2 has 32 to 1, which is like the final prediction for me. This architecture is my own design inspired by the common LSTM architecture in literature, but I tuned up the layer size and dropout rate for my problem. Okay, now we'll go to the time series dataset and the classes and then on the training LSTM. Unlike XGBoost, which sees every hour independently, LSTM needs some sort of a sequence that I created. So the sequence length is defined as 24. Each training example is 24 consecutive hours. The LSTM process the 24-hour timestamp to predict the next value. This allow it to learn temporal pattern like when water rises rapidly, it tends to keep rising. The PyTorch dataset class handle the windowing automatically for me. I don't have to do anything for that. Now, how did we train the LSTM? So the training function used several standard deep learning techniques. First one is the loss function for us, which is mean squared error, and which basically penalizes large errors more than the small ones. The optimizer, which is like Adam optimizer for me, it's an adaptive learning rate optimizer. It, it's an industry standard for us. Now, learning rate of 0.001, starting learning rate is defined as this, and an L2 regularization to basically prevent overfitting on the model learning. Now, learning rate scheduler basically reduce the learning rate by 50% if validation loss plateaus for 5 epochs. Help fine tune the model near convergence. We have used an early stopping, which basically monitors the validation lost. So we have used a patience of 10. Stop if no improvement for 10 epochs and then move out to the next scenario. Prevent overfitting and same training time for me. All these are from the PyTorch library. I configured them. No implementation from the stats for this part. Okay, and how do we handle the NaN values up there? The NaN detection is critical. Sometimes interpolation or feature engineering can create NaN values as well. I check every batch and skip any with the NaNs to prevent training crashes. This is a defensive coding. I added my encountering issues in earlier runs. So the GPU runs. The code automatically detect GPU if available with a CUDA on GPU. Training times is 20 minutes on CPU. The training times is 40 or more than I tested on both. But since I'm using my machine, I tested most of the training on my CPU. Now, so the result, what I want to mention is LSTM performance is comparable to the tree model around 5.6 RMSE for 6-hour prediction. It doesn't dramatically outperform XGBoost, but it provides diversity for ensembling, which we later use. Okay, now we'll move down, and this is just the basic code where it saves the data, all the things in our results. At the end, will it saves the data in our model LSTM result just CSV, which is up here for all the scenarios. If you see, all the naming convention has been defined according to the model name and the model results. We'll get to it later on. Okay, now moving down to the part 5 of using a GNN training. I want to see how GNN performs since it's on the close proximity and we are predicting on Packery channel. It must give some of the relationship that GNN capture. That's my main motive. So to basically capture the spatial relationship between the station. Each station is a node in a graph. Edges connected nearby station. GNN layer propagate information between the neighboring node. They should capture the spatial flow pattern. I use PyTorch geometric library for the GNN implementation. This is a specialized library for the graph neural network. The architecture is similar to the LSTM, but with graph convolution layer instead of the recurrent layers. Due to the time, I won't go deep into the GNN code, but the results show it performs similar to the other models. 7 centimeter of RMSE for 12-hour prediction. That's what it does. And we have created a node. We did the training of GNNs and then the prediction of GNNs for all the scenarios, then saving the results same as it did if you go open the model. The GNN prediction result has been saved up here for all the scenarios. Okay. Now, lastly, we did an ensemble modeling for all our scenarios, and basically it loads predictions from XGBoost, random forest, LSTM, and GNN, computes weighted average. I use equal weight of 0.25 each and then evaluates the ensemble model performance. The ensemble typically improves RMSE by 5 to 10% over the best single model by averaging out individual model errors. For 12-hour prediction, ensemble achieve a 6.5 RMSE compared to the 7 for the individual models. So if I open up my model scenario, if I show all model scenarios up here, this is the final result I got for all the scenarios and samples with each and everything defined on it. So now moving down to step 7, which is basically testing the data with the blind data that we have for 2025, almost around 10 months of data we are testing with. This is the critical test. All previous steps use 2000 to 24 date 20 2021 to 2024 data. Now I test on completely unseen 2025 data to evaluate real world performance. So here I loaded down both the raw files of the test data given to me on by the professor, and then this is what the date time column feature I used to integrate. So I don't know why weirdly, but the date time column feature is not coming as same as what it used to be on the test and the validation data set. So I just changed the name change to it and then implemented the same thing. So I basically loaded 2025 data, apply the same exact feature engineering pipeline from step 2 that we have done. This is critical. Any difference in pre-processing would invalidate my test results. And then I handled the missing data. So missing data is being filled by an hybrid filling from the base data. So I've used a forward filling up to 12 hours, backward filling up to 12 hours, zero filling as last resort for me. This is imperfect but necessary for a real world deployment for me. I load I load all the trained model from their PKL and PTH file and generate prediction. Each model make prediction for all the three scenarios on the same data sets. So if you see, we are saving the PTH file and the PKL file for all the models for all scenarios. And here is my final results based on the PKL and the PTH file on the test data of 2025 that we are using. So scenario ones, basically model performs similar to the validation, 2 to 3 centimeter of RMSE. For the 6 hour scenario, slightly degradation, 6 to 7 centimeter RMSE versus 5 to 6 centimeter in validation. Step 3 is more degradation, 8 to 9 centimeter RMSE versus 7 centimeter in validation. What I believe is this degradation is expected. 2025 may have different patterns, what we have seen in 2021 to 2024, but the relative ranking of the model is consistent. Ensemble and random forest performs the best for me. In that case, it took me about 10 to 15 minutes, including feature engineering and all model prediction. Then the last thing where we validate most of our thing is creating the plots. So I have created around 10 plots, and you can see how we have compared with the DPI of 300. And yeah, these are the 10 plots that we have created: model performance, performance heat map, validation time series, test 2025 time series, validation scatter plot, test scatter plot, validation error distribution, test error distribution, validation versus test, and the summary of the performance. I'll show you each and every plot one by one, and you can find the plots up here. This is like the model comparison for me. So if I can see, this bar charts compare RMSE across all models and scenarios. Key insight, like clear degradation with the forecast horizon. Persistent is competitive at 1 hour but fails on the later hours like 6 hours and 12 hours. Ensemble is consistently among the best for all the hours. As you can see, even for the 1 hour, Ensemble gives almost similar results with the persistent. And random forest, surprisingly, it performs strong. Now going down to the heat maps. This heat map show all the matrices like RMSE, MAE, R square, color coded. Green is better, red is worse. Easy to spot that. All models achieve an R square of greater than 0.97 for 1 hour scenario. R square basically drops to 0.85 for 12 hours. Ensemble has the most consistent performance here as well. So you can see up there. Now, plot 3 is my time series for the first week, second 12-hour scenarios and 6-hour scenarios as well. Same visualization, but for 2025 data. Sorry, this shows 1 week of prediction versus actual water level. You can see all models track the journal pattern well. Different emerge during the rapid changes. Might be a storm event. The 6 hour prediction lags slightly behind the rapid rises. LSTM and xgboost have similar behavior, as you can see for all the. So if I'll zoom in into each plot and then show it. So yeah, so the actual is the black one, and the red dotted pattern is the XGBoost. The mustard color pattern is random forest, and the green is the ensemble one for all the three scenarios. Okay, so plot 4, um, similar plot, same visualization, but for the 2025 dataset. This model still tracks well, but with slightly larger error due to the extreme events. The color coding is same as we did for the validation data set, and you can see the actual one and the predicted one. Okay, step 5 is my scatter plot for all the models, XGBoost, Random Forest, LSTM, and Ensemble. Predicted versus actual scatter plot. Perfect prediction would lie on the diagonal line. Notice a tight clustering around the line for 1 hour for all the models. For 1 hour for all the models, then the 6 hours, and then the 12 hours. So more scatter for 12-hour predictions, and no major biases errors are symmetric around the line. A few outlier due to the extreme events that we have. Now, coming down to our plot 7, and sorry, the plot 7 is for the test prediction. See, you can see there are major deviation as we did for the validation data set. Now, plot 7, which is my validation error distribution, the histogram of predictive error. Now, error are roughly normally distributed, which is a good sign for me. Mean error near zero, no symmetric biases. Tail shows occasional large error, probably storms, and XGBoost and RF has similar error profile up here. Plot 8 is an error distribution, but for the test data. But for the test data here, you don't see a normal distribution because it is not normally distributed. We have larger errors on the test part. And then, then there is validation versus test comparisons for all the models. And you can see XGBoost is in pink, blue is LSTM, uh, blue is LSTM for validation, pink is LSTM for test, and in symbol is on mustard colors. And you can see for all the horizons we are getting this. And on the below one, you can see an operational reliability and model improvement for all the horizons. Okay. Uh, on my last plot, we have a table summary for all the scenario which model performed the best. So you can see scenario 1 has a good performance from persistent and ensemble, almost similar. For scenario 2, we are the good performance came from XGBoost 22.98 centimeters for RMSE, and then scenario 3 we have LSTM 21.57, which actually performs well as compared to the scenario 2. Uh, so all the plots use Matplotlib and Seaborn libraries. The plotting code is fairly standard. I configured color, label, and layout, but using the libraries plotting function directly. So my step 8 basically took me around 5 to 10 minutes to generate all the plots. Now, how to run this whole pipeline if anyone want to validate the code and to test it, you just go to the analysis code, go to the directory, go to analysis code, run step 1 for data quality. If you have a newer data, then do a and do run a step 2, which is like advanced feature engineering for a feature engineering part. Then do a train baseline model on step 3, and then train LSTM on step 4. Step 5 is training GNN model, and step 6 is creating an ensemble model. The naming convention is basically giving you a sequence how to load and test for each files. Step 7 is my testing of the data, and then step is like generating all plots. The dependencies that you need to rerun this code again is pandas, numpy for data manipulation, matplotlib, and seaborn for visualization, scikit-learn for ML model and matrices, xgboost for gradient boosting, optune for hyperparameter optimization, torch for pytorch for LSTM and GNN, torch geometric for GNN extensions, and openpyxl for Excel file reading. Actually, the file is in CSV. I have to convert it back to the Excel, our test file. So if you want to install, pip install pandas, numpy, matplotlib, seaborn, scikit-learn, xgboost, optuna, torch, openpy, excel, and torch geometry. The data requirement is you need to have a 2024 data, since my code has been hard coded for 2021 to 2024 because of the train validation and test split thing. So yeah, that's it. That's it for my side. This is how the whole code has been designed and organized. And if you have any question, just reach out to my GitHub repository or open a PR on that or contact me directly. Yeah, that's it. Thank you so much.